Hi, welcome everybody to my recorded talk. In this talk, I will describe a fairly general technique for approximating two-node connectivity network design problems, which means we want to find some two-node connected subgraph that satisfy some additional property. So I'll describe two problems. So let's start with the first problem. The first problem that I will consider called the block tree augmentation. And in this problem, we are given a tree and an additional set of edges on the same node set. And the goal is to find a minimum size set of edges such that when added to the tree, results in a two connected graph. So I would like to emphasize here that I am considering here the node connectivity version of the problem and not the edge connectivity version of the problem. So we want a two connected graph and not just a two edge connected graph. For example, the three blue edges here do not form a feasible solution. If we add these three blue edges to the tree, then we obtain a two-edge connected graph and not a two connected graph. On the other hand, if we add these three blue edges to the solution, then the resulting graph will be two connected. And actually, we can find here a smaller solution, a solution of size 2, adding these two blue edges to the tree gives also a two connected graph. This is actually the optimal solution here, and its value is 2. So what do we know about this problem, the block tree augmentation problem? The problem admits approximation ratio 2, and this can be achieved by several techniques. For example, either by primal dual method or by iterative rounding. And there are also other techniques to achieve approximation ratio 2. And this ratio 2 applies also for the weighted version of the problem when the edges that we want to add to the tree have weights. In '95, Samil Kuller, in his survey about connectivity problems, posed an open question of achieving ratio better than 2 for both edge and node connectivity variants. For the edge connectivity variant, the so-called tree augmentation problem, this was achieved long time ago, and the currently best ratio for the problem is 1.46. There is also this one approximation, 1.46, is based on linear programming, but there is also an efficient 1.5 approximation algorithm. And in addition, there is also a 1.5 plus epsilon approximation when when the edges have weights, but the weights are bounding by a logarithm in the number of nodes. So there was a substantial progress for the edge connectivity version, the tree augmentation problem. However, achieving ratio better than 2 for the node connectivity version, the block tree augmentation problem, remained an open problem. So in this talk, I will describe you an approximation algorithm for the block tree augmentation problem with approximation ratio 1.91. And the proof idea is a reduction to a seemingly harder problem that is called the subset Steiner connecting dominating set, or for short, SSCDS. And this problem can be described as follows. Given a graph and an independent set R of terminals, we need to find a subset of non-terminals that induce a connected graph and dominate all the terminals. So, for example, if we take this, the yellow triple of nodes, F1, F3, and F5, then they form a feasible solution to this problem. They induce a connected graph, and in addition, they dominate all terminals. Every terminal has a yellow neighbor in the graph. In general, this problem is as hard as the group Steiner tree problem. So of course, the group Steiner tree problem it probably does not admit a constant approximation ratio and probably no ratio better than log square n. However, the reduction instances, the instances that arise from the reduction have some special properties, which I will describe later. And recently, Birka, Grandoni, and Damelli showed that such instances of the subset Steiner connected dominating set problem admit ratio 1.91. So this essentially will finish the proof because we have a reduction to SSCDS, which is approximation ratio preserving, and the instances that arise from the reduction have special properties, and whenever we have such properties, we can get ratio 1.91. So we get ratio 1.91 also for the block 3 augmentation problem. So I will briefly describe the reduction. The node set of the reduction graph H is the set of non-tree edges plus the leaves of the tree. The leaves of the tree are also the terminals. For example, R1, R2 are the end nodes of F1. Hence, in the reduction graph, F1 is connected to both R1 and R2. In addition, for any two edges such that their path in the tree share an edge, there is an edge between the corresponding non-terminals. For example, the paths of F1 and F2 share the red edge. And therefore, there is an edge between F1 and F2 also in the reduction graph. So this is the reduction, and the key observation is that F is a feasible solution to the block 3 augmentation instance if and only if F is a feasible solution to the SSCDS instance. So we have here a reduction and approximation ratio preserving reduction. So another key point is that the reduction instances have two special properties. The first property is that the neighbors of every terminal induce a clique. For example, consider the terminal L2 and its neighbors, F1, F2, F3. Then these neighbors induce a clique. So why is this so? Because if you look at the tree augmentation instance, if you look at the node R2, then any two edges incident to R2, the corresponding path in the tree share an edge, the edge that is incident to R2 in this tree, the leaf edge of R2. So this is the reason why the neighbors of every terminal in the reduction graph induce a clique. In addition, the second property is that every non-terminal has at most two neighbors, two neighbors in R, in the set of terminals. And the reason for this is actually obvious, and it is that any edge connects at most two nodes. And in particular, it connects at most two leaves, which are the terminals in the reduction graph. So for example, consider F2, the edge F2, it connects one terminal to a non-terminal. It connects one leaf node of the tree to a non-leaf node of the tree. And therefore, it is connected in the reduction graph just to one terminal, which is R2. On the other hand, the edge F1, connects two leaves of the tree, And therefore, the corresponding non-terminal F1 in the reduction graph is connected to two terminals, which are R1 or R2, but more than two is not possible, because any edge can connect in the block tree augmentation instance, can connect at most two leaves. So these are the properties, and as I mentioned, the Birka, Grandoni, and Damelli proved that such SS-CDS instances that have these two properties admit ratio 1.91. So this actually finishes the proof that block tree augmentation admits ratio 1.91. So we are done with the block tree augmentation problem, and further details can of course be found in the paper. And I'm now moving to the second problem that can be handled essentially by the same method. And this problem is called two connected dominating set, or oops, just a second. Okay. It's called the two connected dominating set, or 2CDS for short. So in this problem, we're given a graph, and we want to find a two connected dominating subgraph of minimum size. A minimum size can be the number of nodes or the number of edges. It does not matter, because in a two connected graph, the ratio between the number of nodes and the number of edges and the number of nodes is at most 2. In a two connected graph, the number of edges is at most twice the number of nodes, and it is at least the number of nodes. So the objective can be to minimize either the number of nodes or the number of edges, and all this is up to a factor of 2, and while the ratios I will claim here are just actually polylogarithmic, so it does not matter. So the motivation for this problem is constructing a cheap fault-tolerant virtual backbone. So let me illustrate what this problem actually wants to find. It wants to find a subgraph that is both two connected, and any vertex that is not in this subgraph is dominated by some vertex in the subgraph. So for example, this is a solution, the yellow nodes here form a solution of value 4. So first, the yellow nodes induce a two connected graph, a cycle, it's a two connected graph, and every vertex that is white, every white vertex is dominated by some yellow vertex. So the yellow vertices form a two connected dominating set, or I can say that the subgraph induced by the yellow vertices is a two connected dominating set, and the value of this solution is 4, actually independent whether we want to minimize the number of edges or the number of nodes. So actually we can find here a better solution, a solution of size 3, or value 3. Here we have a subgraph induced by the 3 yellow edges, yellow nodes, And it's a two-connected graph, the subgraph induced by the yellow nodes, and moreover, every white vertex has some yellow neighbor in this graph, so it's a two-connected dominating set. This is actually an optimal solution in this instance of value 3. And this problem is related to many problems, and it is to many problems that have a polylogarithmic approximation ratio. So one problem is the dominating set problem, which is essentially a set cover problem, and it has a tight ratio log n. Another problem is the connected dominating set problem, which is essentially the node-weighted Steiner tree problem. And it also has a tight ratio log n. Two connected, two dominating set problem. I will not show it here, but this was done before, also admits a tight ratio log n. And as we should see, this problem was also related to the problem we discussed, the subset Steiner connected dominating set problem, which is related to the group Steiner tree problem and admits approximation ratio log to the 3n. Actually, a long-standing open question is, can we get some non-trivial, say, polylogarithmic approximation ratio for the two connected dominating set problem? So I will really briefly describe how this can be done, and what I prove in the paper is that this problem, the two connected dominating set problem, admits expected ratio till the O of log to the 4th n. So expected ratio, it's a randomized algorithm, and the tilde here above the O means that we suppress the log terms. And the proof idea here is a bit more complicated reduction, a three-stage reduction. So the two connected, the three stages are as follows. We first reduce the problem to a problem called dominating block tree. So dominating block tree is a problem that is closely related to the block tree augmentation problem. But here, instead of augmenting a tree, we seek both a subtree and an augmenting edge set that makes it two connected. I will describe this in several seconds. And next, we reduce the dominating block tree problem to the subset Steiner connected dominating set problem in the same way we have done before. And finally, we reduce the SSCDS problem to the group Steiner tree problem. So how do you get this ratio log to the 4th? So the first step in the reduction from the two connected dominating set problem to the dominating block tree problem invokes a ratio of roughly log n. And this is done by a result of Abraham, Bartal, and Neumann that shows that there exists a distribution of spanning trees with a stretch roughly log n. So one log n factor is the first reduction, and another log to the 3rd come from the fact that we can solve the group Steiner tree problem, that the group Steiner tree problem admits a log to the 3rd n approximation algorithm. So let me describe to you what is this, the first step of the reduction. What is this dominating block tree problem? So in this problem, we are given a graph and a spanning tree. And we want to find a minimum size subset of edges of the graph, and also a subtree of the given tree, such that the union of the subtree and the edge set is a two-connected graph, and moreover, the subtree that we find dominates all the vertices. So for example, if we consider this instance, and we pick just a single edge, F, and we take also the subtree of the red edges. So we take the blue edge and subtree of the red edges. So this is, this solution will not be feasible because the tree, the nodes of the subtree that we have chosen does not dominate one vertex, which is the vertex, V3. V3 is not dominated by this small subtree. So this is not a feasible solution. This is a solution of value 1 because we just, the value is the size of the augmenting edge set, not of the entire subtree. On the other hand, we do have here a feasible solution of value 2. If we take the red tree and the blue edges, the two blue edges, then we get a two-connected graph, and the nodes of this two-connected graph dominate all the other vertices in the graph. Actually, we have here a solution of value 1. If we take a single edge, V4, V5, then and the tree that is formed of the path between the end nodes of this wedge V4, V5, then this will be a two connected graph, and it dominates all the other vertices of the graph. And I will not describe the other steps of the reduction. It's not so simple, but it can be found in the paper. So let me summarize what we have here. We have a method that works for several problems. It approximates two-node connectivity problem, the network design problems, by using a reduction to the subset Steiner connected dominating set problem. So what I've shown here that the block, with this method, we show that the block tree augmentation problem admits ratio 1.91, which breaks the approximation barrier of the natural approximation barrier of 2. And we also showed here that the two connected dominating set problem admits a ratio tilde O log to the fourth n, which is the first non-trivial approximation ratio for this problem. And there are some additional problems in the paper that essentially use the same method. So there is a crossing family augmentation problem, and there is two connected quota subgraph problem for which there is a log squared n approximation algorithms, tilde O of log squared n approximation algorithm. And so what you can see here is that either we can improve the existing approximation ratios or get the first non-trivial approximation ratio for the problem, or quite easily obtain approximation ratios that are not too far from the best known ones. So this is the end of the talk, and thanks. And if you have any questions, I'll try to answer them. Bye.